We're going to kind of step away from the drone technology here, talk about a little bit more about the planning process and how we can use that to be proactive, specifically when we talk about our long span complex bridge inventory. But I will say that I can see where that type of technology could be implemented into these risk-based inspection plans as a complement to our field inspections and overall inspection product. Start off, I'd like to recognize a couple of my colleagues that helped me pull this presentation together, Mr. Barry Colford and Mr. Shane Bibas, both of AECOM. So, why do we inspect bridges? I mean, as best as we reasonably can, we want to ensure the structural integrity of the bridge, to keep the users safe, minimize disruption, and manage the asset. Being a Philly guy, it's always good to reference Benjamin Franklin. An ounce of prevention is worth a pound of cure. So you guys are doing great work out there, and it's good to see. So we talked a lot about this yesterday, and I don't have to go through the history again. National Bridge Inspection Standards establishes a biennial inspection frequency, gives the bridge owner and the states tools to increase the frequency, ensures uniform coverage. It's really developed to allow us to manage large groups of bridges. We've implemented, new for fracture critical and also underwater inspections. It does address complex bridge procedures in the NBIS, talks about special inspection procedures, also talks about having additional inspector training or experience. And then there's been certainly a more recent, although not very recent, but more emphasis on element level inspections. Federal Highway come up with the 23 metrics to evaluate the NBIS program. Metric 19 also is one of the metrics that specifically addresses how we approach the inspection of complex bridges. Let's talk a little bit about risk management. It's often, in the media, it's often mixed with outcome. Risk is the effect of uncertainty on objectives. More specific to bridge inspections, it is the product of probability of the occurrence of the event occurring, consequence of the event occurring. It can be very subjective when we assess risk or evaluate risk. To properly manage risk, we must first identify those risks. And then we come up with a management plan. It's coordinated activities to direct and control the risk. They cannot always be avoided. We do our best to mitigate them. And overall, for it to be effective, there needs to be an effective management strategy. When we evaluate the risk, we identify them, analyze them, evaluate and respond for each of them. We talk about risk management for bridge inspections. A risk-based inspection program has generally been adopted in other industries, oil, gas, chemical, energy. The risks are mitigated through the establishment of a risk-based inspection program. Takes into consideration the characteristics of the assets and the impact on the public. But we have to, an important concept of that is the establishment of what failure is to that particular asset. And when we talk about bridge inspections, it's no longer performing its intended function to safely carry loads or maintain serviceability. So if we looked at risk-based inspection plan as an alternate approach for our complex bridges, one of the things that we would look at would be to evaluate the the assessment of the criticality, vulnerability, and current condition of each bridge group, or each bridge component or groups of components, carried out to determine the frequency of the inspection based on the risk of failure, and it can take into account the defect, or take into account the difficulty of determining or identification of the of defects through the inspection process. So this is beneficial in three ways. It allows us to identify those elements that are most at risk for failure. These will be inspected more frequently. It allows us to utilize our resources and staff more efficiently. And increasing the inspection frequency on our critical components assures the long-term structural integrity of that component. So developing a risk-based program, we determine our priorities and objectives, minimize the risk of safety of the public and the bridge staff, ensure the long-term structural integrity of the bridge, minimize disruption, establishes and focuses management resources to those most in critical components. So there's three main risk headings that we want to consider. Risk to life or serious injury, the risk of catastrophic structural collapse, which of course may also result in the first risk occurring, and then the risk of operational capacity or serviceability of the structure. If we're going to evaluate the risk of life, I mean, one of the methods is the fatality accident rate, which is the risk of death per 100 million hours of exposure to that activity. This is just a quick example of how you could how that's used. And with each fatality, there can also be serious injuries and/or significant financial costs. So acceptance of risk, it's very subjective, varies over time. All bridge owners would likely agree that they primarily must be to ensure that the risk of structural collapse is minimized. But the more difficult choice is balancing the risk of injury or even potential loss of life against disruption of significant disruption. So the risk-based program, it's at the owner's discretion. It can be as simple or as complex as needed. It takes into consideration the current condition of the bridge. Again, the frequencies would vary from those prescribed. But the most important thing, and I think we've heard that over the last day or so, is that communication is key, and consultation and discussion between all relevant parties involved has to be that first step. Again, we want to determine the vulnerability of each bridge component, and it's based on its failure mode, likelihood of detection, probability of failure occurring. We also want to assess the criticality of each bridge component, the effect of the failure of the component would have on the structure and the bridge user. And it's something that's important, yet often difficult to accept, is that the highly likelihood does not necessarily mean high risk if the consequence is small, and conversely, the high consequence does not necessarily mean that it's high risk if the likelihood is small. We can look at it from a failure mode, effects, and criticality analysis. Your acronym is FMECA there. Each component is assigned a quantitative score based on a defined criteria that you determine that's unique to your structure, and it results in the assessment of a risk priority number. And then we rank these elements and highlight those of the most concern, and this allows us to determine the proper or the minimum frequency of inspection of each of these components. It highlights the most probable modes of failure. The FMICA process can be carried out on all the bridge components. And important concept to understand is that it's subject to reassessment after any future assessment or load rating, and certainly after each and every bridge inspection. Again, it takes that current condition of the asset into consideration. And it will vary, the level of risk will vary over time based on the influence associated factors, the condition materials, and the age of the bridge. I mean, if you just took a quick example of a suspension bridge and some of the bridge elements or components that we would look at, the suspender rope sockets, it's a highly critical component of a suspension bridge, and it's also an area where we see a lot of deterioration, and it's certainly something that we want to, where the inspection frequency would be more frequent than every 2 years. Whereas the length of the suspender rope, we're anticipating limited change cycle to cycle, and that inspection frequency can expand beyond the 2 years. Same goes for the external steel of the towers. Again, limited change, and that frequency could be increased. When we say when the frequency can be increased, it could be, we're still doing the visual inspection. It's just the hands-on or the more in-depth level of effort. We talk about level of vulnerability and criticality. Vulnerability is assessed quantitatively, subjective scoring determined, likelihood of detection has to be considered, and it's based on the availability of access for inspection, whereas criticality considers and quantify the effect of the failure on the safety of the public and the staff, the effect of the integrity of the bridge, the effect of the disruption on the traveling public, economic impact. For those of you aware, the Pennsylvania-New Jersey Turnpike connector bridge that crosses over the Delaware River recently had a fracture of a tension member. It was closed for a couple months while they did an emergency repair. I think the repairs came out about $12 million, but they also were losing $1 to $2 million in toll revenue each week. So those are the kind of economic impacts that have to be considered when we're evaluating risk-based approach, and then also the effect of the reputation on the bridge owner. So we take that information. Criticality score is the maximum score. Vulnerability score is the square root of the product of each vulnerability rounded up. So you come up with a table like this, and it gives you a minimum frequency of inspection as we evaluate each of the bridge components. So in conclusion, what we're saying is that for our long span complex bridges, a fixed frequency-based program may not be best suited for our long span complex bridges. Bridge owners are looking for an alternative inspection strategies. Risk-based inspection methods have many advantages, where we target and prioritize the most critical and vulnerable elements of those bridges, and we increase those inspection frequencies. And then there's an additional advantage, and this is significant, where we are making the best use of our bridge inspection resources, whether it's staff or money or technology, to reduce that risk to both the bridge user and the bridge staff.